You've probably heard, or even pondered, the thought that we're just a tiny speck in this vast, endless universe. A flicker in the grand cosmic dance. Well, recent scientific findings are adding a surprising new chapter to that idea. Researchers from the University of Hawaii have made history by mapping a colossal supercluster of galaxies, a mind-bogglingly massive region of space where our own galaxy, the Milky Way, resides. This enormous cosmic void is growing at an alarmingly rapid pace, and what's even more astonishing, our galaxy is being swept along for the ride. I am Earth, and I've been drifting through the cosmos for eons, spinning and orbiting in a never-ending celestial waltz. Right now, I'm spinning on my axis at over 1,600 kilometers per hour, depending on where you're standing. But that's just the beginning of the dance. I race around the Sun, which itself is blazing a trail through the Milky Way galaxy. And the Milky Way? It's not sitting still either. It's hurtling through the local group of galaxies, and we're all being swept along by something even bigger. But here's the real twist in the tale: we're speeding toward a massive cosmic structure, the Shapley supercluster. It's a collection of galaxies, an immense, densely packed conglomeration of cosmic matter. Yet, strangely, something doesn't add up. There simply isn't enough mass in Shapley to explain why we're moving this fast. Half of our journey through the universe is an utter mystery. We're being dragged by some invisible force, but where is it taking us? What's pulling us, and, more mysteriously, what's pushing us through the universe at breakneck speed? In 2017, a team of scientists made a stunning discovery that might just hold the key to the puzzle. They proposed the existence of a cosmic region that could very well explain the bizarre motion of our galaxy. But here's the kicker: it's not pulling us, it's pushing us. Sounds like something out of science fiction, right? But, strangely, it's backed up by evidence. Let's dive in, shall we? To begin, it took astronomers a long time to even realize that we were moving, let alone figure out why. For centuries, we assumed the stars we saw were simply distant objects, scattered randomly across space. But then, in 1924, an astronomer named Edwin Hubble proved that those stars were actually entire galaxies beyond our own Milky Way. His groundbreaking discovery shook everything we thought we knew about the universe. But as exciting as this was, it was just the beginning. Over the next few decades, astronomers, including Stephen Gregory, La Thompson, and William Tiff, showed that galaxies weren't just scattered everywhere, they were actually organized into superclusters, gigantic groupings of galaxies connected by vast cosmic filaments. Superclusters are so massive they span hundreds of millions of light-years across, and yet, despite their size, nearly 95% of all galaxies are located within these enormous structures. Our own supercluster, known as the Laniakea supercluster, wasn't mapped in detail until 2014. Surprisingly, even though we live in it, studying our own cosmic neighborhood proved to be much harder than expected. Why? Because the Milky Way is in the way. Our galaxy is thick with gas and dust, blocking our view of the far reaches of space, particularly when we look toward the dense center of the Milky Way, which is so packed with material that scientists have dubbed it the zone of avoidance. This zone is incredibly tricky to peer through, making it tough for astronomers to get a good look at our nearby cosmic surroundings. Studying galaxies further away is easier because their light is traveling through relatively less obstructed space. But to truly map our corner of the universe, we have to scan every point in the sky, which is no small feat. Despite these challenges, astronomers have made significant progress. By analyzing the peculiar motion of galaxies around us, scientists have been able to group them into superclusters and map their interactions. These peculiar motions give us clues about where we are in the universe and how we're moving relative to other galaxies. At the heart of our own supercluster lies a mysterious and powerful region known as the Great Attractor, about 150 to 250 million light-years away. The Milky Way, along with many other galaxies, is slowly being pulled in this direction. However, the Great Attractor is concealed within the zone of avoidance, making it extraordinarily difficult to observe directly. The plot thickens. Our galaxy is not only being pulled toward the Great Attractor, but the entire Laniakea supercluster is itself hurtling toward another massive structure, the Shapley supercluster. Here's the next twist in our story. We've been tracking this motion for a while, but scientists discovered that the mass we observe in these regions isn't quite enough to explain the sheer speed at which we're moving. There's a discrepancy. So, in 2017, a team of researchers from the University of Hawaii took a radical approach. Rather than just mapping the galaxies, they mapped the motion of galaxies. They created a flow map of the local universe. After running their data through complex mathematical models, they uncovered something completely unexpected. While much of the motion of galaxies pointed toward the Shapley supercluster, they also discovered a significant amount of mass moving away from a specific region of space. This region was dubbed the dipole repeller, and yes, it's as strange as it sounds. The mystery deepens. The motion of our galaxy, the Milky Way, is equally influenced by the gravitational pull of the Shapley supercluster and the repelling force of the dipole repeller. How can something push? In a universe dominated by gravity, that sounds impossible. Here's where things get mind-bending. Instead of the dipole repeller pulling us, it's more of a pseudo-force, a curious imbalance in the fabric of space. Imagine a perfectly balanced universe where galaxies are evenly distributed. Gravity from every direction would cancel each other out, and we'd be stationary. But when one side of that balance is empty, like in the case of the dipole repeller, gravity from the denser regions starts to pull harder, creating the illusion that we're being pushed away from the emptiness. It's not so much that the void is actively pushing us away, it's that the lack of mass in the void allows the gravitational forces from the denser regions to act more strongly on us. But that's not all. The universe isn't just expanding, it's accelerating. And in regions of high mass, like galaxies and clusters, gravity slows down that expansion. But in voids, where there's little to no matter, expansion proceeds without resistance, making the voids swell as the surrounding areas of denser matter are pulled toward them. This unchecked expansion might create the sensation of a push. So, could this expansion of the voids be linked to dark energy? Dark energy is a mysterious force thought to make up about 68% of the universe's total energy, and it's accelerating the expansion of space itself. While scientists have understood dark energy's presence for decades, its true nature remains elusive. Some cosmologists believe that dark energy might be more pronounced in low-density regions like voids, where there's less matter to resist its push. It's an exciting thought, and if the dipole repeller is truly tied to this phenomenon, it might reveal new insights into dark energy's role in the universe's future. By studying the behavior of voids like the dipole repeller, scientists could gain a better understanding of how dark energy operates on both local and cosmic scales. We might even be able to answer bigger questions: is dark energy a constant force across the universe, or is it more dynamic, changing over time? Though the dipole repeller is still a topic of debate, future observations using ultra-sensitive telescopes might allow us to detect the faintest galaxies within this void, confirming its role in shaping our cosmic motion. As we continue to map the universe, every new discovery, whether it's a galaxy, a black hole, or a mysterious void, brings us one step closer to unraveling the ultimate mysteries of the cosmos. And perhaps, just perhaps, we'll begin to understand not just the pull of gravity, but also the mysterious